First and foremost, I would like to thank Department of Physics, Namche Government College and Sikkim University to provide this platform to make this topic Newton's Law of Cooling. I would like to express my gratitude to Dr. C.P. Khatewara for partial fulfillment of Bsc third semester June to December 2020. This video carry 25 marks for sessional examination. Myself, Doma Sherpa, bearing roll number 19 NS0134. Now, I would like to extend my topic, that is Newton's Law of Cooling. It states that the rate of cooling of the body is directly proportional to the temperature difference between body and the surrounding, provided it to be very small. So, mathematically, we can write it as the rate of cooling, that is the change in temperature per unit time, that is dt upon dt, is directly proportional, that is directly proportional to the temperature difference between body and the surrounding, that is T minus T naught. This is the temperature difference between the body temperature and the surrounding temperature. For example, we have the rate of cooling in case of 80 to 60 is greater than the rate of cooling in case of 60 to 40. What it actually conveys is that R1 is greater than R2, means greater the temperature, the rate of cooling will be higher as compared to low temperature. If the temperature is high, the rate of cooling will also be high as compared to low temperature. So, Newton experienced the same thing and he finally arrived at this result. At Newton's time, there was no Stephen-Boltzmann law or any precise technique that would measure the object's radiation. Still at that point of time, Sir Newton came to this contribution. So we can prove this. So before proving, we can convert this proportionality into equality, that is dt upon dt is equal to k t minus t naught. The Newton's law of cooling says that the rate of cooling, rate of cooling. So during cooling, the temperature will always decrease. There is a decrease in temperature. So during cooling, if the temperature decreases, then dt upon dt will be less than 0. So here the rate of change of temperature per unit time will be negative. And here k, this k has got a positive value. This k is nothing but a positive constant. And here this T minus T naught, the temperature of the object is greater than temperature of the surrounding. So this has also got a positive value. Here both the thing is positive. Both the term is positive, and we know that if the temperature of the object is greater than the surrounding temperature, then the temperature of the object decreases. So this term will be negative. Here is a decrease in temperature because the temperature of the object is greater than surrounding temperature. So the negative sign is over here. So it has got a negative sign. The negative sign is over here. where T is the temperature of the body, T naught is surrounding temperature, small t is time, and K is a positive constant. So we can prove the Newton's law of cooling using Stefan-Boltzmann law. If T and T naught are the temperature of the body and the surrounding respectively, and A is the surface area of the body, then by Stefan-Boltzmann law, the rate of heat due to radiation is del U is equals to E sigma A T to the power 4 minus T naught to the power 4. If del T is the temperature difference between between body and surrounding, then we can write del T as T minus T naught. If we can write del T as T minus T naught, then T, which is the object's temperature, we can write it as T naught plus del T. So here we get the value of T. So substituting the value of T over here in this equation, we have del U is equals to E sigma A T naught plus del T to the power 4 minus T naught to the power 4. In a more simplified way, we get E sigma A. Taking T naught to the power 4 common, we have 1 plus del T by T naught to the power 4 minus 1. So, Newton's law of cooling comes with the condition that the difference of temperature is small as surrounding temperature. That is, T minus T naught must be small. If the value of del T is less in comparison with T naught, that is the surrounding temperature, then we can apply binomial approximation over here. We can apply a binomial approximation. So using binomial approximation, we have del U is equals to E sigma A T naught to the power 4 this power 4 gets multiplied over here. We know 1 plus x to the power n can be written as 1 plus nx. This is the binomial expansion. Binomial approximation can be applied over here only when the value of x is very less than 1. Likewise, over here the value of this term is very much less than 1. Since del t is less than the surrounding temperature. So further in a more simplified way, we can write it as a 4 del t into t naught to the power cube. How? This 1 and 1 gets cancelled, since 1 minus 1 is 0. So this t naught gets cancelled with 1 t naught over here. Then we can write it. Now in more simplified way, further we can write E sigma A, 4 E sigma A t naught to the power cube del t. We can mark it as equation number 1. Now heat released by the object is given by dq is equals to minus of ms dt. Here dq is the amount of heat lost by the object. Now then its corresponding effect will be its temperature decreases with dt amount. Since the temperature decreases and hence the minus sign is over here, further dq upon dt is equals to minus of ms dt by dt. Let us mark it as equation number 2. We know that del u is equals to dq upon dt, which means del u is the amount of heat lost by the object per unit time. So let us club equation number 1 and 2. So from 1 and 2 we get minus of ms dt by dt is equals to 4 e sigma a t naught cube del t. Further dt is equals to 4 e sigma a t naught cube by ms del t. So dt by dt is equals to minus of k t minus t naught. Hence Newton's law of cooling is being proved using Stefan-Boltzmann law. Here this term is nothing but the constant k and del t minus t naught, that is the difference of temperature of the body minus surrounding temperature. Hence the Newton's law is being proved. Here this constant k depends on the surface involved. The kind of surface involved is area of the surface, emissivity of the surface, and specific heat capacity of the surface. And this constant k also depends on the surrounding condition, that is T naught. So again, looking back to Newton's law of cooling, we have the rate of cooling, that is dt by dt, which is slope slope of T, that is temperature versus time T, small t. And this dt by dt, it is directly proportional to the temperature difference between body and the surrounding, which is T minus T naught. So here this T naught has got a constant value, and looking forward to the graph, if the object's temperature is less, then the slope too will be less. If the object's temperature is less, then the slope will also be less. And if the object's temperature increases, then the slope will also increase. If the object temperature is over here, then the slope too will get increased. If with the surrounding, the temperature of the object gets equal, then the rate of change of temperature will be 0. dt upon dt will be 0 only when the temperature of the object gets equal with the surrounding temperature. This is the Newton's law of cooling. Now here I end my video. Thank you.